Hello Internet, my name is Quinn and this is Blondihacks. This is Mill Skills, a series of quick videos on getting started with your vertical mill. This is episode 8, aligning the spindle to a hole or punch mark. Let's go. Let's start with the why. As a beginner, aligning a mill with a hole on a part might seem like a trivial thing, but it's actually one of the most fundamental operations you end up doing in your setups. It's a very common thing that you wind up needing to do. There's a bunch of reasons for that. First of all, holes are often made on other machines. You might have started on the drill press or on the lathe, and now you need to come over to the mill and maybe you need to create a feature, some kind of a shoulder or a flat area relative to a hole. So then, you need to start by aligning the spindle with that hole so that you can traverse relative to that hole and get your feature where you want. Another common operation might be if you've got a part that you've bought or that came with some piece of machinery and you need to modify it in some way. And again, the hole is your reference. Maybe you need to enlarge that hole and you want to make sure that the new hole is properly centered where the old one is. Or maybe you're fabricating a bracket for something and you've got a hole that didn't line up in quite the right place. You want to make it into a slot, so you want to line the mill up on that hole so that you can mill out a slot. Or if you're working on a part from a print and if it's symmetrical on multiple axes, it's quite common for the primary datum on the part to be in the center, often where there's a hole. So if you've done some operations on this part and now you need to come back and do other operations, you need to know where the center axis of the part is, but now there's a hole there, so you can't indicate on it in any useful way. And you don't necessarily want to edge find and then do the math to find the center, because that's going to be less precise than if you can find a way to indicate precisely the spindle on the hole itself. The good news is there's lots and lots of ways to do this, all with varying levels of precision that we'll talk about, and I'm going to show you a few of my favorites. Let's start with a very intuitive and simple approach, which is, I think, most people's go-to, including my own, and in most situations this works very well, and that's to simply get a pin that's the same diameter as your hole, and then put that guy in, say, a Jacob's chuck on your mill, and then we simply bring down the quill and manipulate the table until that pin goes down in the hole, just like that. Now this seems intuitively obvious, and for new machinists this might seem like as perfect as you can get. What could possibly be wrong with this, right? Well, it turns out there are a lot of sources of imprecision in this, so if done well, this method is precise to less than 1,000th, but there are a lot of sources of error, so most of the time you do this, it's probably going to be a little less precise than that. The most obvious source of error, of course, is that this whole thing depends on how well the pin fits in your hole, and, well, in this case, not that well. So that's why I was able to get it to go in there so easily. This is a 1/4 inch dowel pin, and this is ostensibly a 1/4 inch hole, but whoever made this hole did a pretty lousy job, and that's not a great fit. This is probably, 10,000ths of play there. So that's obviously a source of error. We're not going to get centered to any better than 10,000ths just because of that. But even if this dowel pin was a good fit, there's other sources of error. It's going to matter if you're holding this pin in a Jacob's chuck or in a collet or other method. Jacob's chucks are less precise than other methods of tool holding. That's going to be a factor. The precision of this pin is going to matter. This just happens to be a piece of 01 tool steel that I've cleaned up the ends on. But if you used, say, a proper gauge pin, it's going to be much more precise. This pin might have a bend to it. It might not be obvious, but if you put this guy on the surface plate, and if you see any light under it anywhere, it's got a little bend in it. That bend could be 1/2 thou or more. So all of these little sources of error are going to add up to where this method, may end up only being, say, 5,000, somewhere in that neighborhood. But for many, many operations, that's more than good enough. And of course, the obvious advantage of this approach is that it's incredibly fast. Here's another example where the pin is a very good fit in the hole. It's actually tricky to get it in there. So that is like, that's like at least an RC2 fit. There's no lateral play in that at all. So this is obviously going to be more precise, barring all the other sources of imprecision that I mentioned. So let's get this guy in there, see how we do. So when the pin is a better fit, this is obviously a lot trickier, but you have pretty good feel on the quill. Oh, there it goes. Now it's going in, but I can feel that it's tight, so it's not quite centered. There's friction on one side or the other. So I'm manipulating that a little more. Still tight. There we go. It loosened up. So now that's going to be quite well aligned. That's probably within a couple thousandths. And with any of these methods, once you've got it aligned, you want to go ahead and zero out your DRO and or your hand wheels so that you can come back to this spot as you need to. A common variation on this trick is to use a drill for this because, well, drills come in lots and lots of sizes, and so you can probably find one that's a good fit for your hole. So here's one that's a much better fit for our oversized hole than the 1/4-inch dowel pin was. But there are a few mental traps to watch out for if you use this method with a drill. The first, of course, is that drills are quite flexible, so it's easy to be 4 or 5 extra thousandths off and not realize it because the drill is simply flexing. And the longer the drill is and the thinner the drill is, the more susceptible you are to this trap. The other common trap is that you might be inclined to use the drill that made the hole to realign on that hole. However, drills tend to cut oversized. They are not precision tools by any stretch. So the drill is always going to be a little bit of a loose fit in the hole that it just made. And if you're new to machining, that might sound like horsey talk, but there's tons of reasons why drills cut oversized. First of all, again, the flexibility that I mentioned. It's fairly easy for them to wander in the hole, and there are various techniques for minimizing that. But the other common reason is that there are 2 cutting edges on the bottom of a drill, and they're never exactly identical, so one of them is always going to be doing a little more work than the other, and that tends to push the drill slightly off course as it goes. And the drill might just be bent, or it might have some run out in it, it might be poorly made, lots and lots of reasons. Again, drills are not precision dimensioning instruments. They are bulk removal tools, so be careful about using them for a precision operation like aligning on a hole. But hey, in a pinch, it works, and you've seen me do it on this very channel very recently. And all of that is why I keep these guys around. This is just 01 tool steel that I've cleaned up the ends on, as I said. And you keep these in, a lot of common sizes, 1/4-inch, 3/8, whatever. If you're in a metric shop, maybe you have 3mm, 5mm, 10mm, 13, etc. And these guys are going to be not quite as precise, obviously, as precision ground gauge pins, but they're going to be a lot more precise than something like a drill or other methods. And you're probably going to find that 99% of the holes that you make are going to be one of these standard sizes anyway, so take advantage of that and keep some pins around. Another good source of field expedient dowel pins is your transfer punch set. These guys also come in a million sizes. And unlike drills, they're smooth all the way down, which is frequently very convenient. So once again, you can just chuck this guy up in a collet or Jacob's chuck, depending on the size. And then we can use this guy to align on our problematic oversized hole. And there she goes. In terms of precision, the transfer punch method is going to be between drills and dowel pins. These guys are relatively precision made, and the smooth sides are going to give you more precise alignment. They are still a little bit flexible because they are long, but they are less flexible than drills because they are meant to be hammered on. So what is the upper bound of this method? Well, if you do everything right, if you have a precision ground tool steel dowel pin that's a precise fit in your hole and it's mounted in a collet or even better directly in the spindle of your mill using an R8 tape or something like that, if you do everything right, then you can get within half a thou of perfect alignment on that hole using this method. Now, why would you ever want to go to all of that trouble? This is why. One of the most common reasons to need to align your mill to a hole is to set up a rotary table. You want your mill spindle to be exactly centered on the axis of rotation of the table. And this is such a pain in the patootie that you will often see a rotary table hanging out down at the end of the mill table on many a machinist's mill. They've set it up once down there, they went to all the trouble to do it perfectly, they saved its location in the DRO, and then they don't ever want to move it. So a great Saturday afternoon project is to go over to the lathe and make yourself a very precision dowel pin that fits exactly in the center of your rotary table and then has an R8 or something that will go in a collet on the other end and can be used to align your rotary table to, say, better than 1,000th in mere seconds. Now, what if we need a little more precision, or if the hole is larger, then the dowel pin method becomes a little impractical. Maybe you can't make a pin that big that will also fit in any type of tool holding in your mill. So what else can we do? I kid, I love woodworkers. In that case, it's time to get serious. And we start by putting away childish tool holding and go to the collets. This is your basic dial test indicator. This is a half thou resolution, but obviously the more precise indicator you use, the more precise this method will be. And we're going to use the round shank holder on the end of it here in a collet. Now obviously the end of the indicator is not in any way aligned with the spindle axis, but that doesn't actually matter. What matters is that the offset of that indicator tip is going to be concentric with the spindle. As long as that indicator is rotating concentric to the spindle, we can use it for what we're about to do. Now, as with anything on the mill, the more retracted and the more locked everything is, the more precise this will be. So ideally, you'd want to lock your knee or your head, and you could do this with the quill, but ideally you would have the quill fully retracted and locked, again, for maximum precision. But a lot of the time, that level isn't required, and this method is still going to be more precise than other methods. Now, the trick here is that, of course, any indicator has a limited range of motion, and so we need to get this indicator in the ballpark of being centered on that hole such that as this indicator rotates, the indicator remains within its range of reading. If it bottoms out or lifts off of the bore that we're trying to indicate on, then all hope is lost, and cats and dogs living together start stockpiling toilet paper. So an easy way to do that is to simply bring the indicator down just above the hole, like so, and now you can rotate this guy around and see how close you are. So I need to move this way, and I can see him quite off in that direction, so I'll go this way. And once you get to a point where the tip of the indicator is roughly the same distance from the edge of your hole all the way around, now you can start thinking about going down into that hole. And of course the arms on these guys are adjustable, so we can just bring this guy in. And you want to bring this guy in such that it'll be riding on the edge of your hole, and the indicator will be within its range and not lifting off the surface or bottoming out at any point. And once you get into that sweet spot on the travel of the indicator, which is a little fussy to set up, but now we can sweep around by rotating the spindle by hand, and you can see that we're effectively measuring how far off of that bore the spindle is. Now, how do we use this information to get aligned on the bore? Well, that might seem difficult because we can rotate this guy arbitrarily and we get crazy readings all over the place. The fact is the table only moves in 2 dimensions. All we have is x travel and y travel. So all that really matters is what our reading is aligned with the x and aligned with the y. So what you can do is rotate this guy so that the travel of the indicator is aligned with the x-axis on your mill. Now obviously if you're not perfectly aligned with the x-axis, there's going to be some error introduced by this step, but if you're careful and align it by eye in both directions, it's actually going to be pretty precise, as you'll see. So what I can do is make a note of this reading, or if you like, you can zero it in this position, and then head on over to the other side, rotate the indicator around, paying attention to the direction that the needle's moving as you do this. Get it aligned with your x-axis again. So we were at 0 on the other side, and as we came around, the needle was moving clockwise, so we're at 15 plus 4, we're at 19 thou on this side. So we want to split the difference between those two readings. We want that needle to go down to, let's say, about there, and then we'll go check the other side again. We'll spin this guy on around, coming back. There, and we were at 5.5 the other way. Now we're on about 7.5, so we're getting close. So we're going to split that difference again. Right there. So we're on 7 right there. And then back around this way. And we're on 7 there. So we're looking good on the X. And now we do this same exercise on the Y-axis. Now once again, I check the reading here after aligning it with the axis. And if it makes it easier, you can zero it on each move. But now we have a problem. Go to flip it around the other way. Now what do we do? Well, that's where our friend the inspection mirror comes in, so you can see it when it's facing backwards. But of course, you're looking into a mirror now, so you can get messed up on what direction the needle is traveling. So this takes some gray matter to pay attention to what you're doing. And after a few minutes of fiddling around with that, we've got it within half a thou here all the way around. I can't show you all the way around, obviously, with the camera, but you could fiddle around with this more and get it better than that. You could, at this point, maybe switch out to a tenths indicator if you really need it dialed in. So this method is fussy, but it is very precise. At this point, you might be thinking, wow, that was incredibly fussy and tedious, and there has got to be a better way to indicate precisely on a bore, some sort of dedicated special purpose tool. And then you started thinking of all kinds of crazy contraptions that would solve that problem. Trust me, none of the ideas you're having right now work. Luckily, people smarter than both of us have thought about this problem, which leads us to the Cadillac of bore indicating options, the coaxial bore gauge. This is the distinguished option for the refined machinist, or maybe you just have more money than time, or you don't relish the idea of contorting your body all over your mill table for 10 minutes every time you want to indicate on a bore. So let's look at this guy. Now, just like the budget-conscious indicator option, this guy also mounts in a collet in the spindle. Let's take a close look at how this guy works because it is really very clever. Now, indicators, of course, measure linear travel. They're a clockwork mechanism, right? So what we need is a way to measure concentricity with a linear measurement device. That's a pretty tricky problem. So the way this guy works is there's a leg down here that rides in your bore, and there's a little rocker mechanism here. And that rocker mechanism is translating the horizontal motion of that leg into vertical motion in this indicator. If you look at this gap right here as I do this, you can see how the whole body of the mechanism is moving up and down. So what we have here then is a way to measure horizontal variance using a linear indicator. And that's really what we need. So how do we translate horizontal variance indication into concentricity? The answer is we do it dynamically. And I'll show you how that works here in a second, but the setup is very similar to the dial test indicator. You need to get the range of travel of this leg within the range such that it will be riding on your bore surface, but not being overextended in any direction. And the trick is, unlike the dial test indicator, this guy doesn't have that friction adjustment to where you can position the arm. Instead, what they give you is a whole range of these little legs that you can install here. So there are straight ones in all different lengths, there are curved ones in all different lengths. And these guys can be used to measure both interior and exterior round objects. So the curved ones are typically for exterior surfaces, but they also work for interior ones, especially on small mills. Because the trick with this guy is that you are using the length of the leg to change the range of travel of the leg. So these legs are a lever. Your fulcrum is this little rocker mechanism here. So the longer a leg on there you have, the further this guy is sticking out, the more range of motion you have at the tip of that guy for the same amount of travel on this rocker. So the idea is you choose a longer leg for a larger bore, and you move the head of your mill up to get the tip of it in the right position. However, on small hobby mills like this, you often don't have that much room to move up. So that's where these curved legs are also very handy for measuring larger internal bores on a small mill. But officially, these guys are intended for exterior surfaces. So step one is to figure out which leg is going to give you the range you need for your bore, and then position your knee or your head vertically in the right place to get that leg aligned on your bore surface. To do this, I use the same starting method as we did with the dial test indicator, which is to position that leg above your bore and then rotate it. And there's no risk to any mechanism here because we're not touching anything. So you can rotate it and visually see by eye if you're describing a curve that's very similar to the circumference of your circle. And then you can move this leg by hand to get a sense of how much of a range you have on that. So that short leg was too short because it was entirely inside the bore and it wasn't going to be touching when we moved it down. So we'll go up to the next size up leg, and well, here's the small mill problem. This leg is too long and my head is all the way up. So that's where we go to the small curved leg. An easy sanity check here is just to move the leg by hand on opposite sides of your hole and make sure that the mechanism isn't going to bottom out on either side. And then we can just ease our leg down into the hole, like so. Now in principle we could turn this guy and get our readings But of course, it has the same problem as the dial test indicator did in that we can't read the dial when it's facing away from us. So the clever compromise to that problem is that the body of the indicator is free spinning, and it comes with this little leg that we can attach. And then you just need something to hold that leg to keep the whole thing from turning. You can hold it with your hand, or I like to just put an indicator stand in there, and that'll keep things in place so we have both hands free. So now you can see how that leg is following the bore, and as it does that, that needle moves back and forth. And remember, that's measuring horizontal variance of that arm. Remember, on the question of how do we convert horizontal variance into a concentricity measurement, I said the answer was dynamically. And that brings us to the craziest part of this tool, which is that you run it under power. Now, you don't have to. You can turn the spindle by hand, but generally running it at a low RPM when the variance is large and then a slightly higher RPM when the variance is small makes it easier and quicker to dial this guy in. You never want to run it too fast. Probably 200 RPM is as fast as you'd ever want to run this guy. So this is 50 RPM right here. Now, what we're doing is we're looking at the swing of that needle. And what we want to do is minimize the movement of that needle. So you grab an axis, any old axis, and you move it slowly, and you watch to see if the swing gets larger or smaller. So it got larger there, so I'm going to go the other way. And as I crank this in, I'm using the y-axis here. You can see the variance is getting smaller. The needle is swinging. And what will happen is you'll get to a point where the needle will start swinging larger again. And that means you've gone too far, so it's time to stop with that axis. If you still have variance, then that means that the remaining variance is being caused by the other axis, so it's time to switch to the other one. So I'll go to my x-axis here. Okay, the variance is getting larger, so that's the wrong direction. So I'll go back the other way. And you just fiddle back and forth with the two axes. There's a little bit of an art to this, but you'll develop the feel for it. Once you get good with this guy, it's very quick to get this dialed in. And once again, when you get down to a small variance like this, it's helpful to increase your speed a little bit. So that's 100 RPM right there. Because when the variance is small, it's easier to see the range of the needle change if it's moving a little faster. You could fiddle with this and get it dialed in better than that, but you can see that we're within half a tick here of travel on that needle, and these ticks are half a thou of coaxial offset, so we're, probably within 3/10 here of being perfectly coaxial with that bore. So that's the coaxial indicator. Very sexy, great tool if you can swing it. They're not the cheapest things in the world, but if you do this operation a lot, it's probably going to pay for itself in time, headache, and neck cricks. And here's a little pro tip. Sometimes the tool will fall out of the collet as you're loosening the drawbar, and you really don't want to do that with this precision piece of measuring equipment. So the foam from the box makes a great little insurance policy. Now let's look at a related operation, which you often need to do, and that's aligning your mill on a punch mark. This is especially common if you're doing fabrication work, or if you're doing manual layout, you're often going to have a punch mark where you want a hole to be. So how do we do that? Well, one quick and dirty way is our friend the transfer punch again. So similar to what we did with the bore, we can bring this punch down and then very carefully by eye, just line that up with the pointy end of our transfer punch. Of course, this method has many sources of imprecision in it, so it's going to be good to maybe 10,000ths, but for many operations that's good enough. If you're just making brackets for a workbench, fabrication level projects, that's going to be just fine. But of course, this is a transfer punch. It's not a precision tool, so it's very likely to have a bit of a bend in it, or it might be leaning a little bit. And because it's so long, it doesn't take much error up here to move your punch down here a noticeable amount. Again, we're holding it in a Jacob's chuck, another source of error. So not the most precise method, but very, very quick. Here's a variation on that method, which I like a lot, and you've seen me use this on my channel. Put a number 2 center drill in there instead, and then bring that down. And then what you can do is first line the center drill up by eye, and that'll get you pretty close. And then once you think you're close, put some light pressure on that guy with the quill, and just rotate it by hand. And the end of that center drill will make a little machined divot, and you can see visually if that divot is aligned with your punch mark. And if you have scribe lines as well, you can see if the divot is aligned with those. And that'll get you within probably 2 or 3 thousandths. And if you're off a little bit, you need to move it, you go down and you make another divot, and it'll recut your divot a few thou over. And you can just keep doing that until you're left with something that's lined up with your punch mark. This method eliminates a lot of the sources of imprecision of the transfer punch method. A center drill is short, rigid, and precision made, and because it's short, we're in close to the work, so the knee is close or the head is down low, and the truth is always in the cut on anything in machining, and so by turning that center drill by hand and actually carving a little divot, we can really see where the center axis of that cutter is winding up, and by extension where the center axis of the spindle is. I like this method a lot. It's my go-to when lining up on a punch mark, and as I said, it'll get you within a couple thousandths. If you need better than that, you probably shouldn't be using layout and punch marks anyway, but there are a couple of other options. One of the options that comes with most coaxial indicators is this option here. So the idea is you can put this hardened point on a punch mark, and then the combination of this built-in travel here and the rocker motion of the coaxial indicator will allow you to read when you're centered on that punch mark. I have never had good luck with these, to be honest, so I'm not a big fan and honestly don't really use it. Once again, if you need this level of precision, you shouldn't be using punch marks anyway. Now the old-timers are screaming at their YouTube players because I've gotten this far without mentioning the original low-budget old-school way of doing this, the wiggler. I don't actually have one to show you, but I can explain how they work, and I'll link to a great video by Mr. Pete that gives you much more detail. They have a long pointer mounted in a ball at the spindle end, and you run them under power, and it flops all over the place, as you might expect, because it's mounted on a ball, and you bring something in like a pencil, and you use that to straighten out the rotation. It has a gyroscopic action that wants to keep it on the center axis of the mill because it's spinning, and so that gives you a much more accurate pointer than something like the transfer punch, which might have a bend in it. And so you can use that to align the punch with the pointer. And you can also often get a ball end on them as well, and much like an edge finder, that ball has a precise diameter, and so you can use it to touch the edge of a surface, find that, and then move in by the radius of the ball to find your edge. Skillful use of a wiggler can get you within 1 or 2 thousandths of being aligned, so they're a great tool. They do take some practice, but they're also very inexpensive, so check it out as another option. That does it for Mill Skills today. I hope you found something in here useful. Consider throwing me a couple bucks on Patreon, and we'll see you next time.